Hello everyone. In the week 7 of algorithms and data structure, so this is the last week of our course. So let's take an overview that what we have covered yet, right? So let us start with what are the data structures. As we know, the data structures are a way to organize our data. It is the way that we can specialized format it for organizing, processing, retrieving, and storing data. So the structure, how you are defining your data, like you're defining it is linear manner, non-linear, how the data is stored, what is the relationship between the data, and what the operations we can perform on the data. It is something like that you think of a container where you put some data in a specific layout. So if you're putting elements one by one, so you can pick the top one first. If you're putting your elements side by side, then you can pick any element. So it depends on that how you're organizing your data, and based on the organization the operations are defined, that what operations you can define on your data. The common data structures we have with linear data structures and non-linear data structures. The linear data structures includes arrays, linked list, stacks and queues. Non-linear are trees and graphs. And one more we have the hash based, which stores the information in the value form of key value pairs. So arrays which we have worked on, so these are the contiguous memory locations in which we access the elements based on their index, right? So the on the basis of the index values, the elements are accessed, and these are the contiguous data structure. So if we want to add some element or we want to remove, we want to increase the size of the array or decrease the size of the array, it is really little bit complex. So we have the linked list. It is another way of storing the data in a linear manner, but it is non-contiguous in nature. So the different parts of memory, whichever are available, they are found and they're connected via the pointers. They're linked via the pointer, so that's why we call it as a linked list. So each node here contains the data part, which stores the information, and one contains the address part, which contains the address of next node. So linked lists are non-contiguous. Adding an element or increasing the size, decreasing the size is easy since it is non-contiguous, but linked lists are sequential in nature. So like unlike arrays are random in nature, you can access any element directly. But in case of linked list, you need to, if you want to go to the fourth element, you need to start from the beginning. The first element to the second element, then to the third element, then you can go to the fourth element. So linked lists are sequential in nature. Other linear data structures are stacks and queues. As we know, stacks works on last in first out, that is the LIFO structure, and the operations are of stacks are push and pop. Push, inserting an element in a stack; pop, removing an element from the stack. Queues are based on the first in first out, and the operations are NQ and DQ. NQ to insert an element, DQ to delete an element. Then the non-linear data structures are trees and graphs. Trees are the hierarchical data structure. Like we have a in our file system like C drive, then within that several folders, then inside those other folders, then files and so on. So that is a hierarchical data structure. Or if you see in an organization, there is a topmost CEO, then under those sub managers, then more employees and so on, right? So that is a hierarchical data structures. For example, we have binary search trees, we have binary trees, AVL trees, red flag trees, so many. Other non-linear data structure is graphs, which we have covered. So the graphs is a collection of vertices and edges. So all the vertices or nodes, which are also called as nodes, are connected by the edges. It may be any of the shape, any of the size. Like you can think of it as like the cities are the vertices and the roads connecting them are the edges. So that is a graph. Other data structure which we have, that is the hash based. So these store information in the form of key value pair, like one key then the value associated with that key. So it makes your searching operation fast enough. So because if you have the key, you can directly find out its value. Why data structures matter, why we are studying this subject. So choosing correct data structure can drastically improve the performance of an algorithm. If for the right purpose, if you're using the right algorithm, right data structure, then it enhances the performance. They provide you, and once the data structures are defined, so they provide you an abstraction. You can just directly use the data structure in your code, so you have the reusable interfaces. Your code becomes neat and clean, it's easy to understand. Like if I'm using a stack, I can directly use the built-in stack, and I can do the stack.push, stack.pop, like this. We do not need to define these operations. So it provides us a level of abstraction. Then problem solving, yes, many of the problems are basically associated with the specific data structures. Like for example, like we are saying the social networks, which are an example of graphs. If you go for the GPS, that is again an example of graph, because you have to find out the shortest distance between two cities. So that is again an example of graph. Then if you talk about go in a queue to purchase a ticket for a movie or something, that is an example of a queue. So it depends. So the different data structures are designated for different types of problems. So it helps us to solve the problem, specific problems. Now, what are the algorithms? As you have read earlier also, but algorithms are, these are a finite sequence of well-defined computer implementable instructions. So it is a well-defined set of steps to be performed by the computer. The algorithms are written in a plain English language so that you can understand the problem well. It is something like that if you have to prepare something, so the recipe, it is the recipe to solve a problem. What are the characteristics of a good algorithm? Every algorithm should have correctness. That means it should provide you correct output for all the valid inputs. Efficiency, getting output is one thing, but getting output efficiently. That means by using the minimum resources with minimum time and memory. Your algorithm should not take so long to compute something. It should do it in the minimal time. So it should be efficient. Clarity, it should be easy to understand, easy to read, easy to understand, and easy to implement. It should not be complex that you cannot implement it. Finiteness, one of the very important property. Finiteness, that it must terminate after a finite number of steps. It should not be an infinite algorithm. And robustness, that your algorithm should be able to handle unexpected inputs or errors. It should not, it should not show you error, it should handle the errors, right? So what is the importance of efficiency? If your algorithm are efficient, if these can work for small inputs, then these can work for large input also. So these makes your programs scalable. It saves your computational power and battery life, so these help you in resource management, and they directly impacts the responsiveness of applications, so the user experience is good. The next topic was we have covered in the week one with the recursion. So recursion, what is the recursion? If you remember, a recursion is a technique in which a function calls itself. So, and we discussed also that we have the two conditions should be there. One is two cases should be there. One is the base case and recursive case. Base case for which function does not calls itself, and recursive case where the function calls itself with a modified argument which takes it closer to the base case. not far away, which takes it closer to the base case. Because if you do not have a base case in your recursion, it will be an infinite loop. It's not going to terminate ever, right? Like we have the factorial and Fibonacci examples. So for the factorial, n factorial can be calculated as n times n minus 1 factorial with factorial of 0 is 1. So the factorial of 0 is 1 is the base case. And every time if you calculate the factorial of n, you're calling the n minus 1 factorial. So that is the recursive call, recursive case. In the case of Fibonacci, fn equals to fn minus 1, f plus fn minus 2, which is the sum of previous two terms. So it give with the base cases are f0 equals to 0 and f1 equals to 1. That means the first two values are 0 and 1. So these are the base cases. One more example of recursion is binary search. So in which if we have to search an element, we search either in the left half or in the right half of the array. The condition is your array must be sorted. Like if you are having the elements from 1 to 10 in the sorted order, you need to find the 7. First of all, you find the middle element 5. So, okay, 7 is definitely greater than 5. So, we will search in the next half, right half. We will not search the left half. So, every time we divide our array in half, and this process is done recursively. So, whether we should use recursion or we should use iteration. Recursions are good because they provide you very elegant solutions for few problems, for number of problems. Like for trees and graphs, for the trees, recursions are best because the code you can write in just few lines. In 2-3 lines, you can write the complete code for the trees. But the problems with the recursion is there is an extra overhead of function calls and there is an issue of stack overflow. On the other hand, with the loops, these are memory efficient and faster, easy to understand, but it can be sometimes less intuitive for the certain problems. Like again, if I'll say the for the quick sort, merge sort, or if you have to implement the graph algorithms, these are complex to implement via loops. So the rule of thumb is there is nothing like that recursion is good or iteration is good, loops are good. Sometimes in some scenarios loops are good, but in some scenarios recursion is good. So use iteration whenever possible, recursion when it significantly simplifies the code. Then classes. So classes is a blueprint that it defines the how the object will be. So it has a data members which are called as attributes, and it has a member functions which are the methods. Then object is an instance of a class. So whenever a class is defined, no memory is allocated until an object is created. So the class is just a template, it is just a blueprint to define an object. There are few principles related with object-oriented programming: encapsulation, abstraction, inheritance, polymorphism. Encapsulation is bundling up data and methods so that they can operate on data. So, and you can restrict the access to the components of class. So we can, that is why we use the private and public. If we use a private access modifier, the data can be used within the class only. Abstraction is hiding the complex implementation details and showing only the necessary features. Like if you are using a mobile phone, you if to use it you do not need to know how it has been implemented. So that is a level of abstraction. Inheritance is a feature where a new class gets the feature of or the properties of another class. So it inherits a new class is derived from an existing class. So it has its old features, it has the features of the old class as well as it has its own features. So we call it some kind of a specialized class. Polymorphism, the ability of a function or operator to take the multiple forms. Like if we say the area, and if I'm passing the radius, so it should give me the area of circle. But on the other hand, if I'm passing the length and width, then it should give me the area of a rectangle. And if I'm just giving the side, then it should give me the area of square. So every time we are calculating the area, but different forms of based on the different forms, different arguments. So that is the method overloading. So polymorphism having the different forms. Then one more property of object-oriented principles are constructors and getter setters. Constructors are special methods. These are automatically called. We do not call them. These are automatically called whenever an object is created. So the role of constructors is to initialize the data members, that what should be the value of the data members, and make sure constructors have the same name as the class name. So whatever is going to be the class name, the same will be the constructor name. We define the getters and setters, or also we call it as accessor and mutators. So these are the public methods which are used to access the value, that is to read the value of a data member and to modify the value. So by using these getters and setters, we can have a controlled access on our data members. Like for example, we have a car class with attributes, color, model, and methods, accelerate and brake. A Tesla Model 3 object would be an instance of the car class, right? Okay. Then matrices in C++. So matrices are the two-dimensional arrays. So it is a two-dimensional arrays where we are having some rows and columns. So we define a matrix by this syntax, that int matrix rows and columns, where the rows and columns are the number of rows and number of columns, number of rows and number of columns in the matrix. Or since matrices are or arrays are fixed in size, so we can use a vector of vectors to define a matrix. Like if we have to initialize a matrix, so int matrix 2 3, that means there are 2 rows and 3 columns. So 2 rows and 3 columns are there, 1 2 3 4 5 6. Matrix operations, we can perform all the operations on matrices which we can perform in mathematics, like addition, multiplication, transpose, inverse of a matrix, and everything. But we need to implement all of these. So where are the applications of matrices? Applications are very much used in computer graphics. Like if we have to transform a graph, be in the way of rotation, scaling, shearing, translating, we do all of these operations by using the matrices. If we need to solve the linear equations, those are solved using the matrices. In data science also, when we assign the weights to the neural networks, those are also done with the help of matrices. So matrices are really very, they have lots of applications. Then complexity analysis and big O notation. As we said in the algorithm's efficiency, that it should be efficient. That means it should take least amount of time and least memory. So how can we analyze that which algorithm takes is efficient? So we have certain matrices to identify that, and that is the time and space complexity. Time complexity is how much time your algorithm will take for a standard input n, and space complexity, how much memory algorithm will consume. So the time complexity, how the runtime of an algorithm increases with the size of the input, and space complexity is how the memory uses of an algorithm increases with the size of input. Whenever we execute our programs, we just test them for few number of inputs like 5, 10, 15 and so on. But whenever you go in real life, your input size may be in thousands, millions, even in billion also. So you need to check how your algorithm will respond if such a big data is provided. Right, so the common complexities are big O of 1, constant time, that is the best one. So accessing like for example, if you're accessing an element by an index, you provide the index and access the element, so that is the constant time. Big O of log n, logarithmic time, like binary search, in which we have the input every time in each space. Then big of n, which is the linear time. If you have to search an element in an array by using a loop or something, so that is the big O of n linear time. Then big of n squared quadratic time, whenever we are having the nested loops. Then exponential time is big O of 2 raised to the power n, which is like if you have to calculate the Fibonacci series recursive calculation and all, so that is the exponential time. Then big O factorial n, that is the factorial n time. For example, you are given a list of 10 numbers and you need to find all the permutations of that list, so it will take the factorial time. So what are the best practices for optimization? Profile your code to find the real bottleneck. Prefer algorithm with better time complexities for large n, and be mindful of space-time trade-offs. Abstract data types. So abstract data types is a theoretical model basically that defines the data type solely by its behavior from the user perspective. So it is basically that what operations we can perform, but not how. Like for example, we have certain predefined data abstract data types like list, stack, queue, set, and map. So in all of these, we just use these. These are already defined. So we just need to know that what can be done, what operations list can perform, what operations the stack can perform, what operations queue can perform, but we do not need to worry about that how these operations are performed. So that is the benefit of ADT's abstract data type, that if you have a ADT, you can just directly use it without going in detail that how these are implemented. Like for vectors, C++ provides us STL, standard template library implementations. So STL is std vector we use, std stack for stack ADT, std for q and dq for the q ADT, set in unordered set for implementing the set. A set consists of always unique elements. If you cannot have duplicate elements in a stack, you can have duplicate elements in array, you can have duplicate elements in list, stack, queues, but you cannot have duplicate elements in stack. That is the set. That is the property of set. And map and unordered map, so which are used to implement a map ADT. In map you store the values in the form of key value pair. So vectors versus list. Vectors are dynamic array. So this is a contiguous memory block again, grows dynamically by allocating a new larger array. Like vectors are, if you are have for example, the current size is 5, the current capacity is 5. If the vector is filled, it will automatically grow its size to double, and all the elements will be copied to the new vector. So 5, 10, 20, 40, 80, like this the size will grow. So the size will grow automatically as soon as the capacity is reduced, means the vector gets full. So the and vectors work on index again. So the benefits of using vectors are, these are fast random access via big O of 1 because we use the index, fast insertions and removal, again big O of 1 amortized. The problem with insertion and removal, because if you try to insert any element in between or you try to remove any element from the middle, the rest of the elements we will need to shift to occupy that space. And one more is there, doubly linked list. So it is a non-contiguous nodes. Again we maintain the pointer for these. Benefits are, you can insert and delete element anywhere, any in the middle, in the beginning, in the end, with the time of big O of 1. But the problems are, these are not random access, these are sequential. And sequential, as I told you, if you need to go to the fourth element, you can go via first, then second, then third, then fourth. You cannot go to the directly fourth element. So performance comparison based on which and when to use. So we should use by vectors by default because it is cache friendly and generally faster to use for more cases. But we should use list whenever we require frequent insertions and deletions in the middle of large list, right? Then stacks and queues. So as we discussed that stacks are based on the LIFO principle, but queues works on the FIFO principle, and the operations associated with the stacks are push and pop. So push will add an element and pop will remove the element. Whereas with queue we have the operations NQ and DQ. So NQ will add an element towards the end while DQ will remove the element from the front. Then trees and binary search trees. So trees, we just discussed them last week. So trees are, we have the terminology, tree as is a hierarchical data structure, right? In tree, the root, there is only one root. Node, every element is called as a node. Edges are used to connect the nodes. Parent and child, the same relationship, parent has the child. Leaf nodes, leaf node are if a node does not have any child, then it is called as a leaf node. Otherwise, it is a non-leaf node. And if two nodes share the same parent, then those are called as the siblings. Binary trees in which each node can have at most two children. One is left, one is right. Then those are called as binary trees. And BST trees are also a binary tree, but with a special condition. The condition is all the values of the left subtree should be less than the parent node and the value of the parent node should be less than its right subtree. This condition has to be fulfilled. When we are talking about the traversal method of BST, so we have three traversal in a BST: in order, pre-order, post-order. In order, we do the left root right, in pre-order root left right, and in post-order left right root. Whenever we are having a BST and we perform in order traversal, we get the sorted array. We get the elements in sorted order. Then hashing and hash tables. So hashing is a technique of storing the elements so that we map the elements in such a way that we can retrieve the element in constant time. So basically we require a hash function to perform the hashing. So what are the hash functions then? So a hash function is that converts a key into a hash code which we can uniquely map the element. So the properties of hash function: it should be fast to compute, it should uniformly distribute keys throughout the whole space, and minimal number of collisions should be minimal. If there are collisions, then we need to apply some collision resolution techniques. So we have the separate chaining in which every node, every bucket has an associated linked list, right? Open addressing, which has the probing techniques, linear probing, quadratic probing, and then we have the double hashing. So in this one, we use two hash functions, one hash function plus the other hash function. And then rehashing, for the rehashing, we maintain the load factor, that how much array is filled. If it is filled a certain threshold, then we declare a new array of double size and we apply the hashing again. So that is called rehashing. Then we discussed about some of the sorting algorithms. Sorting algorithms when we need to arrange elements either in ascending order or in descending order. We have done bubble sort, selection sort, insertion sort, merge sort, heap sort, quick sort, radix sort, counting sort, shell sort, so many sorting. So we have two types of sortings basically: comparison based and non-comparison based. So comparison based, in which we compare the elements, like if element is less than or greater than the other one, like bubble sort, merge sort, quick sort. Whereas in non-comparison based, we compare the position of elements. Instead of comparing the values, we compare the position of numbers or certain other properties like counting sort and predict sort. So the complexities like bubble sort, insertion sort, and selection sort have the complexity of big of n square, which is exponential, which is quadratic. Sorry, which is quadratic. So it takes it is little bit complex and costly, I will say. Big of n log n, which is merge sort, heap sort, and quick sort. So these are good. And then counting sort and predict sort take big of n time. Then we move on to the graph theory. So as we said that graph consists of vertices and edges. We can have two types of graphs, directed and undirected. Undirected where the direction are not defined, like from point A to point B and from point B to point A, we can go in any of the direction. Whereas in directed graph, you need to, there is a direction associated with each edge and you can move only in that direction. Then weighted and unweighted graphs, if each edge has an associated weight or cost, then that is called as weighted graph. Cyclic and acyclic graph, if a graph contains a cycle, then that is called a cyclic graph, and if a graph does not contain a cycle, it is called as acyclic graph. Then there are certain shortest path algorithms like Dijkstra and Bellman-Ford algorithm, which are used to find out the shortest path between two pair of vertices or all pair of vertices. Then we talked about the minimum spanning tree. Like from a graph, we want to create a tree which has the minimum cost. So for this one, we use the Kruskal's algorithm or Prim's algorithm. Then one is the network flow problem, in which we try to find out the what could be the maximum flow from source node to the sink node if each has a flow and has a capacity. And we use the Ford-Fulkerson algorithm for this one. Then algorithm design techniques. If we need to design our own algorithm, then there are certain types of algorithms like greedy algorithm, dynamic programming, and randomized algorithms. Greedy algorithms, these are the algorithms which takes the locally optimal choice at each step and then certainly going towards the global. So in this, as the name suggests, these are the greedy approach, these are greedy. So they try to find out the optimal substructure like Dijkstra, Kruskal's and Huffman coding. They does not yield you always the optimal solution, but these are simple and efficient. These are good one. Then dynamic programming is that break out your problem into small subproblems and store the solutions of subproblems in a table which we call as memoization or tabulation, so that you do not need to recompute them. Like for example, in Fibonacci series, if you need to calculate factorial 4, then you will go for Fibonacci 4, then you will go for Fibonacci 3 and Fibonacci 2. Then Fibonacci 3 is again as Fibonacci 2 and Fibonacci 1. So Fibonacci 2 you need to calculate twice. So the dynamic programming says if you have calculated once the value of Fibonacci 2, store it somewhere, and if you need to calculate it again, just take the value from there, do not recalculate it. So there are a number of problems which can be easily solved by using the dynamic programming. Then randomized algorithms are that it uses randomness as a part of its logic. So that the behavior of algorithm will vary depending on the, if the input is same, but still depending upon the random algorithm. For example, the quicksort. If you take the pivot element as the last element or as the first element or middle element or average of the all three or any of the random number, so the performance will change. Then the last one is the amortized analysis. So the amortized analysis is a method to find out the average time per operation over a worst case sequence of operations. So instead of taking the complexity of each and every operation, we take to get the try to analyze the whole the average time over per operation in a worst case scenario. It provides a more accurate picture than looking at a single operation in isolation, especially for data structures that occasionally have expensive operations like vector resizing. Like we said that in case of vectors, once the vector gets fold, we resize, it gets resized to double. So that is included. So average time, we try to calculate the average time. The methods are aggregate method, accounting method, and potential methods. Like as I said, examples are dynamic array doubling or amortized analysis is big of one for this. So the summary of key takeaways we discussed in this one, that what are the data structures, which are the basic building blocks of efficient data organization, what are the algorithms, step-by-step instructions that in English language that how we can solve a problem, big notations that through which you calculate the efficiency of an algorithm, then which algorithm should be chosen when, right? Then because if you choose the correct algorithm, correct data structure, your searching, insertion, deletions, you can check on all the operations. If you have to perform this fast searching, you should use a BST or a hash table. If you need to perform frequent insertion and deletion in middle, you should use a linked list. If you need to perform some operations like FIFO or LIFO, you should use a stack or queue. If you need to use hierarchies or networks, you should use trees or graph. So it depends that which type of problem you are solving, and accordingly you should choose your data structure. Like if you talk about the real world applications, B trees are used in databases very popularly, GPS navigation, graphs and digestra, social networking, again graphs for friend connections, caching we use for hash tables. So these are the real world examples. So that's all for the week 7 and for our data structure syllabus. The book you can refer is the C++ programming language. And if you want to go for the online resources, go for Geeks for Geeks. Every concept is there with a number of examples. Try to practice on LeetCode or HackerRank. There you can build your profile by solving the number of problems, and you will know how to solve the problems. Then if you want to go for online resources, online courses, you can go for Coursera or edX. So that's all for this course, and then we'll see you in the algorithms 2 subject. Till then, take care and goodbye.